Now in matrix multiplication, it is possible that a product, A times B, is the zero matrix even when the matrix A is not the zero matrix and the matrix B is not the zero matrix. Now if A and B are both square matrices of order n, then these non-zero factors whose product is the zero matrix are called zero divisors. So let's look at an example. Let the matrix A be the 2 by 2 matrix with columns 0, 0, 1, 2, and let B be the 2 by 2 matrix with columns 3, 0, 4, 0. Then the product A times B has entries 0 times 3 plus 1 times 0 and 0 times 3 plus 2 times 0 in the first column, 0 times 4 plus 1 times 0, and 0 times 4 plus 2 times 0 in the second column. This is the 2 by 2 zero matrix. And so the square matrices, the 2 by 2 square matrices A and B, are zero divisors. And in matrix multiplication, the cancellation law does not necessarily hold. That is, if the product A times B is equal to the product A times C, this does not imply that the matrix B is equal to the matrix C. So let's look at an example. Let the matrix A be the 2 by 2 matrix with columns 0, 0, 1, 2. Let the matrix B be the 2 by 2 matrix with columns 1, 3, 1, 4. And let the matrix C be the 2 by 2 matrix with columns 2, 3, 5, 4. The product A times B is the 2 by 2 matrix with entries 0 times 1 plus 1 times 3 and 0 times 1 plus 2 times 3 as the first column, 0 times 1 plus 1 times 4, and 0 times 1 plus 2 times 4 as the second column. So this is 2 by 2 matrix with columns 3, 6, 4, 8. And the product A times C is the 2 by 2 matrix with entries 0 times 2 plus 1 times 3, and 0 times 2 plus 2 times 3 in the first column, 0 times 5 plus 1 times 4, and 0 times 5 plus 2 times 4 in the second column. Once again, this is the 2 by 2 matrix with columns 3, 6, 4, 8. So notice that the product A times B is equal to the product A times C, but the matrix B is not equal to the matrix C. Okay, so new definition. Let the matrix A and the identity matrix be square matrices of order n if there exists a matrix B in the set of square matrices of order n such that A times B is the same as B times A, which is the identity matrix of order n. Then the matrix A is said to be invertible or non-singular, and the matrix B is called the inverse of A, which is denoted A inverse. Otherwise, the matrix A is said to be singular or non-invertible, so notice that an identity matrix is its own inverse. Further, if A and B are square matrices of order n, such that their product, in whichever order, is the identity matrix of order n, then A and B are inverses of each other, that is, A is the inverse of B, and B is the inverse of A. So let's look at an example. Let A be the 2 by 2 matrix with columns 2, -1, -5, and 3. And let B be the 2 by 2 matrix with columns 3, 1, 5, 2. A times B is the 2 by 2 matrix with entries 2 times 3 plus -5 times 1, and -1 times 3 plus 3 times 1, in the first column, 2 times 5 plus negative 5 times 2, and negative 1 times 5 plus 3 times 2 in the second column. This is the 2 by 2 identity matrix. And the product, B times A, is the 2 by 2 matrix with entries 3 times 2 plus 5 times negative 1, and 1 times 2 plus 2 times negative 1 in the first column, 3 times negative 5 plus 5 times 3, and 1 times negative 5 plus 2 times 3 in the second column. Once again, this is the 2 by 2 matrix, identity matrix. So the matrices A and B are invertible. The matrix A is the inverse of the matrix B, and the matrix B is the inverse of the matrix A. So let A and B be square matrices of order n, where the matrix A has a column of zeros. Then there exists an index j in the range from 1 to n, such that the jth column vector of A is the n by 1 0 column vector, and so the jth column of the product B times A is the matrix A times the jth column of the matrix A, which is the matrix B times the 0 column vector, which is the 0 column vector. So notice that it is impossible that there exists a square matrix B of order n such that A times B is the same as B times A, which is the identity matrix, and hence the matrix A is singular. So as an exercise, let A and B be square matrices of order n, where the matrix A has a row of zeros show that the matrix A is singular. And as a second exercise, let A be the 2 by 2 matrix with rows A, B, C, D, where the difference of products A times D minus B times C is not 0, and let the matrix B be the scalar multiple 1 divided by A times D minus B times C times the matrix with rows D, negative B, negative C, A, show that the matrix B is the inverse of the matrix A. So next we'll prove a theorem. Let A and B be square matrices of order n if the matrices A and B are both invertible, then the product A times B is invertible, and in fact the inverse of the product A times B is the product of the inverses in reverse order. So proof: since the matrix A is invertible, there exists the inverse of A in the set of square matrices of order n, such that A times A inverse is the same as A inverse times A, which is the identity. Similarly, there exists the inverse of B in the set of square matrices of order n, such that B times B inverse is the same as B inverse times B, which is the identity. So the product A times B times the product B inverse times A inverse is A times the quantity B times B inverse times A inverse, which is A times the identity times A inverse, which is A times A inverse, which is the identity. Similarly, the product B inverse times A inverse times the product A times B is B inverse times the quantity A inverse times A times B, which is B inverse times the identity times B, which is B inverse times B, which is the identity. And hence the product A times B is invertible, and the inverse of the product is the product of the inverses in reverse order.